In this video, we look at one of the most important classes of chemical reactions, acid-base reactions, otherwise known as acid-base neutralisation reactions. When an acid solution is mixed with a base, a neutralisation reaction occurs. Acids, characterised by the presence of H+ ions in solution, react with or are accepted by bases, according to this generalised equation here. The H+ ions from the acid react with the OH- ions produced by bases to form neutral water. Bases are said to neutralise acids and vice versa. Acids are said to neutralise bases. The chemical equation shown here is in fact a net ionic equation where spectator ions have already been cancelled out, leaving just H+ ions and just OH- ions on the left-hand side of the net ionic equation. In reality, we can't have a source of just positive ions or a source of just negative ions. So the source of the H+ ions is always delivered from an acid, for example, hydrochloric acid, HCl, and the source of hydroxide ions is derived from a base, for example, a solution of sodium hydroxide, NaOH. So when solutions of hydrochloric acid and sodium hydroxide react, we can rewrite the acid-base equation as a full molecular equation shown here, where we see that the HCl and NaOH solutions react to produce the ionic salt sodium chloride and water. And we can write a generalised equation to represent acid-base reactions that says any acid will react with any base to produce an ionic salt of some kind plus water. Now, acid-base neutralisation reactions are a very important class of reaction, and you will be required to recall this generalised equation. An acid plus a base gives you a salt of some kind plus water. Acid-base reactions are in fact examples of double displacement or metathesis reactions, and in this example we see that the hydrogen ion from the hydrochloric acid effectively displaces the sodium ion from sodium hydroxide. And these two ions here chemically combine to form water. At the same time, the chloride ion displaces the hydroxide ion so that the sodium and chloride ions come together to form the sodium chloride salt solution. So, we know now that an acid plus a base produces a salt plus water. Let's look at a more complex example by choosing phosphoric acid as our acid and our source of H+ ions, and we will choose barium hydroxide as our base and our source of hydroxide ions. And this, as it turns out, is the first step in writing out equations for acid-base neutralisation reactions. We write the chemical formulas of the two solutions in the form of a full molecular equation. While we know that these compounds actually exist as ions in solution, we want to represent their molecular form so that we understand exactly which two solutions, and therefore which ions, are actually being mixed together in the reaction. Now we know that an acid plus a base will produce salt plus water, so in step 2, we write down the products based on a double displacement metathesis reaction, where we actually swap the anion and cation pairs such that the hydrogen cations from the acid get together with the hydroxide ions from the base to form water. And the cation of the base, in this case barium, comes together with the anion of the acid, in this case phosphate, to form the salt barium phosphate. Now, before we do anything else, we need to make sure the chemical formulas of the products we have written down are correctly written. At this moment, neither of them is correct. If we look at this HOH formula on the right, it is actually the result of a H+ ion coming together with an OH- ion. And when these two ions come together, we know from earlier that they form the molecular compound water. So we will replace the HOH with H2O, the formula for water that we are already very familiar with. In terms of this formula for barium phosphate, we've got to ask ourselves, is this the correct chemical formula for barium phosphate? Do barium ions and phosphate ions come together in a 1-to-1 ratio like this? Well, we know the barium ion is a 2+ ion because barium is a group 2 metal, and the phosphate ion is a polyatomic ion with a 3- charge. So when we use our crisscross method, we can take the 2 from the 2+ charge of barium and put it down as the subscript for the phosphate ion. And we can take the 3 from the 3- ion of phosphate and put it down as the subscript for barium. And so the chemical formula for barium phosphate is Ba3PO4 brackets 2. And so we need to insert the correct chemical formula for barium phosphate into our chemical equation here. So we now have phosphoric acid plus barium hydroxide gives barium phosphate plus water, and all chemical formulas are now written correctly. Now it's time to balance the equation. And remember, when we balance chemical equations, we can only change the stoichiometric coefficients in front of the chemical formulas. And also remember, when we have polyatomic ions involved, as we do in this case, we want to keep the polyatomic ions intact if they exist on both sides of the equation and are not broken down into other substances. For example, we can see that we have one phosphate ion on the left-hand side of the equation and two phosphate ions on the right-hand side of the equation. So we want to keep the phosphate ions intact and balance them as a whole and not as individual atoms. We can also see that the barium ions are not balanced. We have only one barium atom on the left-hand side at the moment, and we have 3 barium atoms on the right-hand side. We also have 3 plus 2, that's 5 hydrogen atoms on the left-hand side and only 2 on the right-hand side. And finally, we have 2 oxygen atoms on the left-hand side, excluding the oxygens that are tied up with a phosphate ion, and we only have 1 oxygen atom on the right-hand side, again, excluding the oxygens tied up in the phosphate ion. So clearly this equation needs balancing. Now, we have had a lot of practice in balancing equations like this. And if we put a 2 in front of the phosphoric acid and a 3 in front of the barium hydroxide and a 6 in front of the water, we'll see that we've now got a balanced chemical equation, same number of atoms on both sides of the equation. The next step is to assign subscripts to our products to determine whether each product is a solid, liquid, gas, or soluble aqueous solution. And we can use our solubility rules to determine if any products will form insoluble salts. In this case, what we've got is the molecular compound water being formed, and that is a liquid. So we put the L subscript next to H2O. Now we look at the barium phosphate. Is barium phosphate a soluble salt and will therefore have the AQ subscript, or will it form a solid precipitate and therefore have the solid S subscript? To answer this, we go to our solubility tables. We look up our solubility rules for phosphate, and we can see that most phosphate salts are insoluble, with the only exceptions being the group 1 metal phosphates or ammonium phosphates. Barium does not fall under either category, so barium phosphate will form a solid precipitate, and we assign it the S subscript. Finally, in step 5, we may be asked to write out the net ionic equation, and to do that, we need to write out the full ionic equation, where all the strong electrolytes are written as individual ions. And then we identify spectator ions and cancel them out to get the net ionic equation. And again, we've had lots of practice with that in earlier videos, with this being the full ionic equation, where both the acid and base solutions, being strong electrolytes, are written as separate ions. Interestingly, there are no spectator ions in this full ionic equation, and so the net ionic equation in this case is the same as the full ionic equation. So, in summary, predicting the products of acid-base reactions. Step 1. We write the formulas of the reactant solutions in the form of a full molecular equation so that we can identify the 2 solutions that have been mixed together, 1 acid, 1 base. Step 2. We write down the products of the reaction based on a double displacement metathesis reaction and the knowledge that an acid plus a base gives us a salt plus water, where the salt formed is derived from the cation of the base combined with the anion of the acid. And at this stage, we need to be sure to write the correct chemical formulas for all products. In step 3, we balance the equation, keeping polyatomic ions intact if they appear on both sides of the equation unchanged. In step 4, we assign subscript labels to the products and use the solubility rules to determine if the salt is an insoluble salt or if it will form a soluble aqueous solution. And finally, if required, we get to the net ionic equation by writing out the full ionic equation and cancelling out any spectator ions present.